Hi, welcome back, everyone, to our Competing on Analytics track here at Data Summit. It's good to have everybody back here with us. Now I have the pleasure of introducing our next speaker. That'll be Thomas Richter, and he'll be talking about big data analytics meets modern data warehousing with open source PostgreSQL. And Thomas is the founder and CEO of Swarm64 in Berlin. He's broadcasting from Berlin as of right now, and he tells us there's a beautiful sunset now appearing on the horizon. So that's one of the cool things about doing virtual conferences. And I understand he's also fluent in 4 languages, and let's make that 5 because we have the language of data we want to add in there as well. So Thomas, pleasure to have you with us, and take it away.
Thank you so much. Okay, so today I want to talk about Postgres, which is, in my personal view, a much underrated data warehousing tool. And hopefully I will leave you with some very actionable tips and tricks on what you can do, how you can use it to its full extent, and also what kind of additional features and extensions you can use in order to extend and just kind of improve its feature base, and thereby make it an even more powerful tool for data warehousing. Now, before we go there, let me just start with a curious observation. What is quite unusual is that Postgres is not really known for data warehousing, yet a lot of famous data warehouses have been built on it. So Netezza, Greenplum, or Amazon Redshift are actually really like for like the Postgres code, forked, heavily modified, and then made available as a data warehousing platform. Now, isn't it curious that these successful products have been built based on Postgres, yet Postgres itself is not really known for data warehousing yet? Because I hope in my presentation, I'll be able to inspire a little bit of curiosity and also talk about some absolutely unique and powerful things Postgres does that actually come in extremely handy when it comes to data warehousing, but they're maybe not on the forefront of what everybody's looking at. Let's see. But before we do that, let me cover a little bit of terminology. So we have on the left-hand side, OLTP, online transaction processing. This is, as you would say, the bread and butter of Postgres. Many different users, connections are interacting with the database and are asking many small queries, like look up that single record, just give me a few values here, and so on. I've got a little update. That's the type of OLTP workload. On the other hand, you have online analytics processing, or OLAP. This is more about insights, queries that ask, okay, how many customers did we serve in the last year? How did our shipments go? Like, what was the average time it took for a priority shipment versus a standard shipment to arrive at the customer? That's the kind of OLAP queries. And then in between the two, you've got what we would call the mixed workloads, or Gartner calls it HTAP, hybrid transactional analytics processing. So that's really just for a little bit of orientation, and probably I'm repeating things to quite a bit of the audience. You're probably very familiar with this. Just to cover a few more bases, MPP, massively parallel processing, just really deploying a very large quantity of computer processors to a problem. It's about parallelism, and it is about preventing things that inhibit parallelism. It can be many computer processors inside a single machine or on separate compute nodes. ACID, the term for atomicity, consistency, isolation, durability, really for making sure that any database transaction survives if it is fully committed, no matter what happens. If there's errors, if there's a power failure, whatever, that's the background of ACID. And then versus ACID, on the one side, you've got eventual consistency, which is a relaxed model of consistency. And that's much more to allow scalability and achieve a high availability. But it also means that you're never sure that data is actually consistent across your cluster. Now, Postgres is very much in this ACID world, in the whatever you provide me is the truth. Eventual consistency is, I would say, more scale out NoSQL solutions. So today we are effectively talking about data warehousing combined with rock solid, reliable ACID. And that's important. I'll come to that later. Quick one also on Rowstore versus Columnstore. Again, just covering some bases here. So let's say you've got your standard table. You've got, for example, this would be the address table. You've got your customer ID that references the customer name, date of birth, and all these things. Then you may have an address line 1, address line 2. You would have the state, the zip code, the country. In a Rowstore, you would read or write along the row. That's, of course, great for OLTP because usually when you're modifying an address, you tend to modify most or all of these columns. Whereas when you're doing an evaluation, for example, give me all the customers in a specific state, you would much rather want to just sort by zip code. You can later on merge in the state, and then you can basically do your evaluation that way. So for example, evaluation by zip code, get the zip code, get the state. I don't need customer IDs. I don't need the address lines. That tells me who has bought how many times in which state, but I don't need the names. I only need quantities aggregated by zip code or by state. And that's what I get from a column store. So a perfect mechanism for asking the kind of analytical question: how much have I sold in any zip code area? How much have I sold in any state? Let's look a little more into the column store. Again, typical state-of-the-art thing is that you compress your data. So as you can imagine, things like states or zip codes, they have a certain degree of self-similarity. So whereas maybe the first value needs to be stored in full, you can possibly store the next value as a delta, as a difference to the previous value. So long story short, they tend to compress extremely well. This is a benefit of a column store as opposed to a row store, where basically the values are behind each other. And in order to compress, you would basically make much longer references, makes the compression much more complicated. So really state-of-the-art mechanism in column stores to get your data together. Now, why would you want to push your data together? Obviously, because when you want to analyze a large quantity of data, you're going to push the limits of what your system can provide. So the less data you have to fetch, the faster you can process. And finally, and now I may be leaving the territory of more general knowledge and probably entering into a little more specific areas. Column stores have nice features that are, I would argue, somewhat column store specific, like, for example, late materialization. So let's say, again, we go back to our example query where we are asking, okay, in which zip codes and in which states were our goods bought? Well, in a way, you may, for example, first aggregate by state, and you don't need the zip codes yet. If this is the case, then you don't need to actually retrieve the zip codes yet. So you could first execute your entire query based on state, and then subsequently, you can merge in the zip codes that belong to each of those states. You could also do it the other way around. But the key point is you're not materializing everything at once. You're first executing the query, for example, finding out, oh, maybe I only want zip codes in this one state. So maybe after you join things together, you will find out that I only need zip codes from a single state. So then it's a great saving that I'm not yet joining in all the zip codes into all the states, but first just execute my query and then pull in the zip codes last. Now, let's change pace here a little bit. So before we were just looking at some general, I would say, techniques that are used very frequently in data warehousing. I now want to make the whole thing a little more Postgres specific. And let's first look at the bright side. What are some of the things that Postgres brings to the table that are in my personal view, underutilized in a data warehousing environment. Let's talk about the first one. Stop chasing ghosts. Asset consistency means that whatever you commit to the database, the moment your transaction is confirmed, is there. That's the truth. So when you're developing and you make a change, and in the next line of code, you're asking the value back from the database, if you don't get the value back that you expect, there's something wrong in your code. In an eventual consistency system, if you write a value and then you query that value and it comes back differently, it doesn't mean there's an error in your code. It could also mean that the eventual consistency system has not yet propagated the value to all of its nodes. So the answer from an eventual consistency point of view is correct. However, it is absolutely incorrect from your programmer's point of view or your developer's point of view that you're trying to test your system. So in other words, you may actually be using days and weeks finding something or thinking you found something when in fact you were chasing ghosts that are based on eventual consistency. One feature that I've not seen much talked about in Postgres in the context of data warehousing is the tremendous amount of rollback features you have. So you can think of rollback in a strictly SQL transactional concept as your super undo. You can wrap everything you have into a transaction, or you can choose to wrap individual pieces into transactions. And then if you make any mistake, you can undo them. You can roll back that transaction and the database will be in the state as if whatever you did had never happened. Example, let's say you're loading in an incredible quantity of data because you're, for example, updating a lot of records, or you're loading in, let's say, last night's sales from all over the country. Now, let's say you made a mistake. Let's say you find that there's some inconsistency in the database. In the data. Let's say there's an inconsistency in the data from an external provider that you maybe merge in. Well, in all these cases, if you find it early enough, you can just roll it back. And that's in a way your undo. Your undo available as you work to undo what you did last and thereby save yourself a lot of time. Postgres goes as far as being able to undo table creations, all these things, index creations, table deletes, etc. There's only a few things you cannot undo in Postgres. That's, for example, like creating a whole database or creating table spaces. But essentially, the undo functions are so rich that they're even exceeding what Oracle offers you. Let's talk about the third one, enforce constraints to prevent errors. So we had the example of the address table earlier. Let's say you're entering an address and the customer ID is wrong. Well, in Postgres, you can set a constraint, and that means it will never allow you to enter an address if the customer ID is not correct. You can make that a constraint. So in other words, I mean, for transactional workloads, that's really bread and butter. But for analytical workloads, this becomes really interesting because it prevents the gradual degradation of your data. Your data may kind of lose quality over time. If you're just collecting without ensuring any form of consistency, you may start off with actually having a very nice and consistent snapshot. And then eventually you'll have lots of ghost customers that actually don't quite match anymore with the actual real orders and things like that. And then your predictions and your analytics become less and less precise. Another example is to use update to make your life easier. Postgres has these wonderful dimensional types, I will call them, like array types or JSONs, etc., which means it's just a single field, but it can contain a whole tree or a whole array of data. So let's say, as opposed to doing it the traditional way that you have a shipment and the shipment has a status, and you're basically keeping a second table that has a shipment status update, and then you're joining that with your shipment table in order to find out what was my last shipment status update, all very complicated. Much easier, keep a JSON object inside your shipment that tracks the order status. Add or update to the JSON object every single step that happened. And then, for example, searching for which shipment was lost immediately after status loaded on delivery truck, that becomes such an easy query. You can do away with the joins. There's no more joins needed. No more mental acrobatics thinking about how do I ask my database this question. It's simply looking up in the shipment status JSON, when did I have a loss that was immediately preceded by a loaded to delivery van. Finally, and this is really just a feature of Postgres being made for fine-grained access, you can just with a very fine-grained single cell kind of precision, correct and delete very quickly. So in kind of these batch optimized solutions, make a small mistake, very difficult to get it out, or time consuming at least. Postgres does, of course, a great job with just lots of fine-grained deletes. Now, where there's light, there's also shadow. And in Postgres case, it is about the skill in the context of this Venn diagram we talked about earlier. So we start on the left, OLTP. It's widely recognized Postgres is absolutely great for OLTP. No question about it. HTAP, mixed workloads. Well, what I've seen is that with increasing query complexity, you require more skill in schema design and in configuration. But you're doing okay leaving your queries as they are. That gets you maybe until about here in the diagram. Once you're kind of crossing over more into the OLAP domain, you should, in addition, be smart about how you write your queries. One of the things I've heard a lot is if you're just using some tools that auto-generate the queries as you need them, you'll basically start seeing a massive performance deterioration. So you're having to be a little more smart about how you write your queries, how you're basically phrasing your accesses, how you're making sure that you don't get into large nested loops and things like that. So, and then you hit 1 terabyte of data or more. So the enterprise grade data warehousing, right? That's like a terabyte of data, or easily 10 terabytes of data, or even more than that, and so on. And then it's just becoming painful. No matter how much you tweak and twizzle with your little query optimizations and trying to be very smart about how you write the queries, you'll just be hitting the limits. A few reasons for that. MPP is limited. Let me start there. So when Postgres is executing, it will scan and filter, it will apply some parallelism. So you see here some boxes happening at the same time. Then you may have a join, again, things happen in parallel. Then you may have a merge that's, for example, based on an aggregate or a distinct. Well, at that point, Postgres may need to put in a serialization point. So that's where your parallelism ends, still with more than half of the query to go. So the next join is happening serial. One single thread. You've got your, I don't know, 128 core machine there, and a single core is busy. Then you've got your sort and aggregate at the end. Again, just one core working on it. It's not ideal. Let's look at the other example, late materialization. So we've said earlier, one cool feature is if you're kind of able to first figure out your query and then pull in the remaining columns when you're done with the query. There's a way in Postgres how you can approach that. And that's what I would like to share with you. It's also one of those tricks that is not so commonly known, but it's working really well. And there's companies that have used this in production. One of them, for example, is AppLovin, or the part of basically Adjust, a company that joined AppLovin very recently. And what you can, for example, do is you could make a type that's like a zip code type. And because zip code and state are really just two permutations of the same thing, right? If you can store a value that indicates where am I, you can derive the zip code and the state both from that value. So in other words, if you apply that, and if you basically make like custom type, you can make sure that custom type aliases to all the valid zip codes and states that you have. As a result, things get a lot more efficient. But you can also see how this is adding complexity. You now need to make sure that your zip code and state are correct. What if there are new zip codes added? Or even worse, look at country. What if your business expands into a new country? You need to make sure that this code type is still valid for that country. So you have greatly improved your processing. However, you have thereby created a maintenance debt to be paid in the future. So hence, it makes more sense to do things like, for example, PG country. It's a custom type you can just download, because countries do change occasionally, like South Sudan and things like that. But it is not the most frequent thing. So certain things lend themselves quite well to being custom data types. And that's a real performance feature if you're analyzing data. Another example we had on that slide was really, so we talked about MPP, we talked about the late materialization ability, but also the column store options. This is now where we look a little bit beyond Postgres. So Postgres is also incredibly extensible. That's a great feature of it. And there are a range of column store options. So I would say the most straightforward in a way is the CStore foreign data wrapper by Citus. A couple of caveats here. Number one, coming from a company that once upon a time also based their solution on a foreign data wrapper, there's benefits to that and there's clear drawbacks to that. So CStore foreign data wrapper can be an option. I would say one should carefully look at the caveats there as well. Very interesting project is ZStore by Greenplum. They are introducing a different table format. So you have the choice then to have your standard table, or you can choose a table using ZStore. This is right now an extension that's on GitHub. I would also claim it is not fully complete yet. They would love to bring this into the Postgres core. There are some debates in the community around that. But even just as an extension, that's great. I am just not sure it's ready yet for prime time. Also, it means you're translating your entire table into a column store format, which you may or may not want to do. Depends. And then you're moving into Fujitsu VCI, vertical clustered index. And this is basically a hybrid implementation. We've got a Rowstore and a Columnstore. And then it basically stores a columnar index in memory. And as far as we know, this is only available for Fujitsu Enterprise Postgres. So it is leaving a bit the realm of open source. We've not been able to find a legal way or really any way to get access to this outside of Fujitsu Enterprise Postgres. And then we have Swarm64. And what we do is, instead of building, for example, another format that has to be accessed via a foreign data wrapper, or forking Postgres and turning it into some kind of enterprise version, we instead decided to really honor all the interfaces Postgres already has and as a result, be able to just plug into standard open source Postgres. And if you think of the blue pieces here being the standard Postgres, and the yellow pieces is what we add. So we add specific features in query planning to rewrite query logic in order to make it more plannable and better to execute in, for example, those heavy complex queries, effectively taking work away from the user that would normally have to rewrite them themselves. We rewrite them in accordance to standard rewriting rules to their logical equivalent. Then there's data access that is greatly optimized with a Columnstore index. I'll explain our Columnstore index a little more in a moment. And then there's query execution, where we decided to increase parallelism, keep parallelism longer, move the data around longer, and, for example, have faster join operations. Now, how this looks in practice is, so you may remember the query we talked about earlier and how this took minutes to complete. Well, in our case, we can shrink this to seconds. We are pushing a lot more parallelism to start with. And also with the Columnstore index, we can skip irrelevant data sections, like, for example, columns that are not needed. The first join gets executed with great parallelism with our own implementation. So they're faster, they need less RAM. There's no serialization point. We just add a shuffle node, and that allows us to then execute the second join immediately after the first without serializing. You can also keep your merge, aggregate, etc. afterwards in parallel. And then finally, your sort and aggregate in the end works faster, just brings the data together, and then you go. You've got your answer in seconds. So why did we choose an index approach? Well, as you could see from us plugging into the standard interfaces of open source Postgres and adding these features transparently to the query, it's very important to keep all the PG functionality untouched. So that means you can still execute all these transactional queries against the native tables, against the existing indexes. And we only duplicate the data that is indexed. So you could say, I want all my columns in the table to be stored in the Columnstore index, or you could say, I want some of my columns to be stored, because typically in my data warehousing queries, I only need a few. Finally, we don't affect the OLTP performance. There is the OLAP queries against the Columnstore, and then there's the OLTP queries running just the way how Postgres has always run them. And that means it's also fantastic for hybrid workloads, because the two do not interfere with each other's work. Don't want to go here. We can cover this in the questions, but it's basically as easy as you basically create index using Columnstore. That's it. You pick the values you want, and that's it. So we'll cover that in more detail in the questions if you like, but basically just a standard Postgres index definition with the using keyword. You're saying that you want a Columnstore index, and then afterwards it will automatically be used in the queries, and it's heavily compressed. This is a more interesting aspect in terms of the hybrid workloads I was talking about. So since the Columnstore index is background updated automatically, can be read much faster, it also means that you can actually run those hybrid workloads on the same database if you wish. And that means that you have zero extract transform load or extract load transform investment. You can do all this constraint enforcement that I've talked about earlier. There's a minimal updates, a minimal overhead with the data updating in the Columnstore. So the Columnstore, this is one of the things we're very proud about, is the ability to modify your data heavily and still be able to read a fresh and accurate Columnstore index. And you always get consistent reads, so you'll never read ghost data. And then finally, you can deliver your reporting and your dashboarding and everything just from the same database. Concluding slide on this, performance difference is very striking. So here, standard data warehousing benchmark, TPCH, 1 terabyte of raw data translates to 2 or 3 terabytes of actual table data in Postgres. Gray is Postgres and red is Postgres extended with Swarm64. You see difference like day and night. It's about sending off a query and having to fetch a cup of coffee, sometimes a 15-minute break before your data returns, or it doesn't return at all, like in this case is here, where it's just running into timeout, versus a few seconds for Swarm64. This is on a standard server. I mean, it's not a cheap one, but it's easily obtainable, and it's very, very economical for your enterprise data warehouse. So let me conclude. Postgres is not very popular as a data warehousing choice yet, because I believe there is limited knowledge in how viable Postgres is now for data warehousing with all its parallelization features that it brought in recently. It additionally takes over some fantastic features that it has from its transactional skills into the OLAP world that can save you a ton of time. Like I was talking about, no more ghosts to chase. You have the ability to enforce data consistency, which means you enforce data quality, the ability to undo, etc. Now, when it comes to larger data sets and complex queries, they tend to require more and more skills and extensive tuning. And this is where solutions come in to make your life much easier. You can get a free developer license from us if you're interested. We also have an AWS 30-day free trial. Now, by the way, you could search for PG Nitrous. I will not require you to remember that code. Or search for Swarm64. Now, one final thing. We absolutely love where Postgres is going. We love the community. We are contributing patches. We've gotten a few patches into PG13, collaborating on patches. I did not put all the bugs here that we found and helped resolve because the slide is already absolutely packed. We are contributing with open source extensions. There's a Parquet foreign data wrapper that we actively forked and published in order to increase performance, and also contributing changes there back to the original version. Also, there's a benchmarking toolkit available that very easily allows you to evaluate Postgres across a variety of environments. And finally, we are working very closely with the community. EDB, a certified partner of us, or we are a certified partner of EDB. Cybertech, the same thing. Command Prompt, Hopla, Nutanix. Yeah, lots of different partners there in the ecosystem. So we do what we can to make Postgres better. We are offering an extension to make it really a serious contender in data warehousing. And I would say maybe one of the best solutions out there for mixed workloads. Thank you very much. And now I'm really looking forward to your questions.
Thank you, Thomas. That was really informative. Thank you very much for walking us through the application, the Postgres, the possibilities with Postgres in terms of data warehousing. And if our members of our audience, if you have questions for Thomas, please, by all means, type them into the chat box on the right-hand side of your screen. And Thomas, will you be available in a few moments in the networking site?
Yes, I'll be joining the networking. Well, once we're done with the questions, and I need a moment to digitally switch rooms. Yeah,
certainly. And it's interesting. You know, we do surveys here at Database Trends and Applications, Unisphere Research. We do a lot of surveys of data adoption, database adoption, and so forth. And Postgres always has a pretty high rank. You know, there's MySQL, and Postgres is probably the second ranked open source database. I should say MySQL. But it's very popular. I wasn't aware of its applications in the data warehousing space. And you mentioned also that there's some forked versions as well, that variants that might also fall under that umbrella.
Well, I would say the most used Postgres in data warehousing is, of course, the closed source Redshift, right, by Amazon, because I mean the wonderful benefit of Postgres code is it's on this wonderfully permissive Postgres license. The downside, of course, is that companies can, if they want, take it private as a fork and build something new, and that's what has happened with what eventually turned into Amazon Redshift through a few iterations. And yeah, I would say this is one of the massively popular data warehousing solutions, maybe one of the top 3 or 4 in the world. And it's so curious that Postgres itself isn't actually the open source, the community version, isn't actually known for its data warehousing skills, which are step by step added and is getting better and better at it. Yet the fork, the derivative, is one of the really popular products in the world. So yeah, that's what we are trying to do, trying to boost the community edition a bit to extend it and make it a much more serious contender.
And how does it integrate? Suppose an enterprise has a data warehouse on Oracle or Teradata or whatever. Is there any integration capability? I know that's probably a a big question, but
yeah, let me try the very high level answer, and then I'm happy to also cover. There's a couple of things. There's a lot of companies we see that say no new projects on Oracle. You may have heard these kind of terms, right? It's more about commercials. It doesn't. I don't want to say anything bad about, because I think Oracle does have a great product. But to quote what we're hearing in the market, they also have a certain degree of commercial aggressiveness. Let's leave it at that. And so quite a few companies have this rule: no new projects on Oracle. So you absolutely are very often in this situation where you have to bring things together. Now, one of the great things about Postgres is the foreign data wrappers. We've talked about them earlier in the context of foreign data wrappers as a means to have, for example, a Columnstore. But you can use a foreign data wrapper, and that's actually the SQL intended way, as a mechanism to access, for example, your Oracle database from your Postgres. So there is means how Postgres can, for example, be the integration layer of your existing infrastructure. And that, I think, is also something that's very, very powerful. It plays nicely with other database sources.
Okay, that's good to know. Good to know. And we're just about at the end of our time. I see we don't have any additional questions, but again, folks, Thomas will be available in the networking chat area. If you want to find out more, get more details about the marvels of Postgres and how to move that forward. And Thomas, we really appreciate you joining us today. It's a great overview and very, very, very educational. Thank you.
Great.
Thank you for
Thank you
being
so
here.
much.